first oral talk of the day is discovery of latent 3D key points via end-to-end geometric reasoning. And Supersorn Suvajanakorn will present this talk.
That's perfect. Sorry, it doesn't show. Okay. Hi, I'm Supersorn from Vistech, Thailand, and this work is done with Noah Snavely, Jonathan Thompson, and Mohammed Norozi from Google. Being able to find semantic correspondence, such as these key points, is part of object understanding and is crucial in many vision applications. Humans are surprisingly good at this task, but this turns out to be very hard for computers because these chairs look very different, and not to mention that we view them from different angles as well. For example, to correctly identify or mask these red points, one has to know which parts are the legs and then understand the orientation of the chair to be able to pick the right leg. Now, what if we ask to pick 10 points? How do we decide which 10 points to pick? Sometimes we can reason about it. For example, we probably don't want to pick the armrest because the other chair doesn't have it. But in general, this is very hard. And it's not quite clear which points will be the most useful for downstream tasks. In this paper, we present an end-to-end geometric reasoning framework to learn an optimal set of key points along with their detectors. Given a single 2D image, our model extracts 3D key points that are optimized for a downstream task. The resulting key points are semantically consistent across viewing angles and object instances and can be discovered automatically without any key point supervisions. Traditionally, the pipeline for geometric reasoning tasks comprises two separate stages. First, we would train a key point detector based on human annotations, then use the inferred key points to predict pose or viewing angles, for example. The first part requires expensive and error-prone key point annotations. So recently, people have been trying to learn key points in an unsupervised manner so that we can avoid collecting labels. Most of the recent work often uses an auto-encoded objective and a reconstruction loss to infer latent embeddings of objects. There's a lot of excitement around these techniques in computer vision and machine learning communities. And people also have succeeded in learning key point detectors, such as LearnSIFT, but so far only in isolation. The problem with that for geometric reasoning is that we never know whether the key points that we have are actually good for the task we're interested in. So in contrast to recent work, our main novelty lies in the use of end-to-end geometric reasoning to learn latent key points. That is, our key points are optimized with respect to a downstream task, rather than being learned through a proxy objective, such as reconstruction. And we use the post-estimation problem as one example of the geometric reasoning task. Here are our automatically discovered key points on test chairs from the ShapeNet dataset. Note that this is a frame-by-frame keypoint prediction using no temporal information. It can also track key points even when they're occluded. And unlike most work, we represent the transformation using real physical 3D transformation and predict key points in 3D. That allows us to match correspondence between two views that are 180 degrees apart that share no visual overlaps. What's surprising here is that the network tends to select key points that have semantic meanings that humans would tend to pick as well. For example, it picks the wheels of the cars, the cockpits of the planes, or the legs of the chairs. And here's how we train our network. Given two views of an object, our goal is to find key points that are best for estimating the relative rotation between them. Here, we pass the two images through our KeypointNet that outputs a list of key points. From the two sets of 3D key points, we solve for the relative rotation between them via least squares, by solving a problem known as orthogonal procrustes. Solving this problem requires computing an SVD, and so what makes this work is the fact that we can differentiate through the SVD operation. And this is the key component here. The loss is then the angular error between the estimated rotation and the ground truth rotation known during training. Another important loss is called multiview consistency loss, which enforces the transform key points from one view to be close to those from the other view, and vice versa using the inverse transform. Now, let's think about architecture a little bit. Ideally, the goal of Keypoint is to have a complete 3D transformation equivariance, but we haven't figured out how to achieve that with our neural net architecture, or whether that's possible at all. And so, however, what we can easily achieve is 2D translational equivariance. In other words, if the car moves to the right by 1 pixel, the key point coordinate should also change by 1 unit. And this can be done by instead predicting a probability distribution map for each key point whose expectation represent the key point coordinate. And second, this requires no strided or stride 1 convolution. And in our case, we use a stack of dilated convolutions to increase the receptive field size. There are a few challenges with unsupervised discovery, such as when the object looks very symmetric like this car. In this case, the network could get stuck in a local minimum where it cannot disambiguate between the two symmetric sides of the car. So one trick that we found works well to help break the symmetry during training is by employing a coarse-to-fine prediction scheme. And one solution that we use is to have the KeypointNet first predict an orientation flag, which says the car is facing left or right, and then condition the key point prediction on this flag and the original input image. This helps the network to track points all the way around the object. There are other generic key point properties that are universally useful for downstream tasks. For example, we don't want 2 key points to occupy the same spot. And we can prevent this by penalizing points that are too close together or points that are closer than a predefined constant delta. Another preferable property of key point is that they should lie on the object silhouette. And this is done by forcing the distribution map to be within the object mass known during training. We also want the distribution map to be peaky so that its expectation lies within the object in case of a non-convex shape. And this is done by minimizing the variance of the distribution map. For this work, we use ShapeNet Dataset to train our network. ShapeNet is a large-scale dataset of 3D objects consisting of around 50 categories and 50,000 unique 3D models. These models, however, have different topologies, and there's no correspondence information between any 2 shapes. Once trained, our network is able to discover and consistently track the heads, the cockpits, or the wings of the planes automatically. And here are failure cases on the bottom, which happen on planes with very unusual wing shapes. Here, the network is having a hard time knowing which direction is front. And here are results on cars. Take a look at the blue car in the bottom, where the key points flip direction. This happens because this car looks very symmetric across 2 axes. So the key points shown here are actually in 3D, and to confirm this and really visualize them, we reproject these key points back onto the 3D model. So these colored key points correspond to the color sphere in the model. Here we show how the network is able to infer the sparse 3D structure of the car from just a single image. More importantly, if we use a supervised pipeline and human annotations based on Pascal 3D, we get this mean and median error in the relative post-estimation. But our pipeline, using 0 key point supervision, produces lower angular errors in the test objects. We also evaluate other metrics, such as how consistent the predicted locations are by computing the standard deviation of the location. So ideally, this column should be close to 0. And our method also outperforms a supervised baseline and predicts more spatially consistent key points on all 3 categories. And here are the error distributions of the 2 techniques. Notice how errors are more concentrated around 0 for our technique. And there are a few outliers at 180 degrees due to the incorrect orientation prediction. Here we show how the model is able to predict key points from any angle consistently, even harder case such as from the side that causes a lot of occlusions for the plane. And here we want to see what would happen if we vary the number of key points. The network is very sensible here, and it starts by discovering the most prominent components, such as the head and the wings, and then gradually tracks more parts as the number increases. And now, to make sure that the network doesn't cheat by just placing key points on a fixed rigid structure, we try our network on these following wiggly cars. So here, the network does use the local features to track parts and successfully predicts where the wheels are and the overall deformation of the car, of the object. To apply this technique to real images, we train the same network, but with a random background taken from SUN 397 dataset. Surprisingly, such a simple modification works on some of the cars from ImageNet. And here we show a few handpicked results and some of the failure modes on the bottom. The network has difficulties dealing with large perspective distortion and cars with strong highlights or pattern. To conclude, we explore the possibility of optimizing latent key points through an end-to-end geometric reasoning framework by taking into account the downstream task. Our network predicts semantically consistent key points across viewing angles and object instances, and now perform a supervised baseline on the task of post-estimation. And a few takeaway messages are that if you have a geometric reasoning task, and you can differentiate through it and train it end-to-end, it can be quite effective and provides a pretty large performance gain. But if you can't differentiate to your task, or if your goal is to do unsupervised learning, you could still consider geometric reasoning as an auxiliary task. Because our world is 3D, and when humans pick up an object from a table and rotate it, we actually have the same kind of relative pose label from the manipulation of our hands. And this is exactly our problem setup. So this task could turn out to be very natural and fundamental, perhaps more than pixel reconstruction for unsupervised learning. Please visit our website for more details, code, and data, and poster number 33. Thanks.
Hello. Hi, this is a very impressive work. So
Thank
I just have very specific questions about propagating gradients through SVD. So one of the questions is because when you're solving least squares, the SVD may give you superior solutions which contains reflections. So do you prune the singular values to rule out the reflection matrices? And secondly, propagating gradients directly through SVD sometimes is numerically unstable. So do you have special approaches to make it more stable during training? Thanks.
So the first question, we did correct for the ambiguity either times 1 or -1. And for the post-estimation loss, in practice, we actually add random noise so that it doesn't run into a degenerate case.
Cool, thanks.
Yes, very nice talk.
Thank you.
I had a couple of questions. Have you tried other data sets than ShapeNet and other downstream tasks than pose estimation?
So unfortunately, we only try on ShapeNet and then on real images, which is from also like a subset of ImageNet, SUNS UG, or SUN 397.
And other downstream tasks?
So this paper only considered the post-estimation task, but they could be other tasks like estimating the scale or the deformation object. Or the other non-geometric related would be, how do you find the best key points for retrieving objects? That would be like a completely different objective, which could be, the same framework could apply.
Thank you.
Thanks.
I have a question. Just a question. You show quickly some real images. Maybe you answered already. I don't know. How do your model separates the background from the main object? So because all the key points were on the main object in the picture.
Oh, so the training for real images, we actually train on synthetic, except it's the same, except we add random backgrounds. So during training, we actually have a little bit signal of where the mask, where the objects are.
Oh, so you didn't do on the image build background.
Yeah, we train on synthetic,
Okay.
but with real backgrounds.
Okay, good, thank you.
All right, thank you.